Hello. So it's been a while, and I'm sorry I could not cover the final exam after the exam. I got lazy at the end of the semester, and I believe you must be busy at the time for the comms, and I hope all of you did well. So let me go over the final exam. The As I said earlier in the semester in the class, the main like of course the main goal of this course is to enhance your econometric knowledge, but I see a bigger problem in your kind of writing, like it's not about English, but so I know that you know what is the OLS estimator, how it works, but the thing is you should be able to write about that. And so the question one uh, is designed to test you, challenge you if you can write down your knowledge. So as you know, this question is pretty trivial. There is nothing special. Everything is standard, and I'm asking you the very simple uh, questions. So simple, but still many of your question answers are not satisfactory. Let me just show you what you had to do. So first, so here, write down the population criterion function and show that beta 0 is the unique minimizer. Here the biggest problem here is, so here I define a criterion function this way. It's a function of beta. And so far, it is just a function of beta. And of course it is a function, so it will have a minimizer. Later we can show that it is convex, so its minimizer is unique. But the problem here is, so far we do not know if beta 0 is the minimum or not. You have to prove that. That's the key point of the proof. What you have to show you here is this. Literally, this is what you have to prove. But most of you just assume that, use it as a fact. Then what's the point of this question? Uh, so you may think it this way. Um, Imagine here, so you can imagine like this. There is a true value of beta 0 that satisfies the assumptions. That's one thing. And here is another thing. Theoretically I define this kind of function, and then this function can be minimized, and there is another minimum. So there is a minimum. So this minimum in the end equals to the true value. That's what you have to prove. But before you prove that, you have to treat them as different objects, right? Again, beta 0, the true value, is defined by the assumptions. And the minimum is defined by this function. So later you have to show they are the same thing. And it's pretty simple. The second order condition satisfied, globally satisfied. So the function itself has a unique minimum, and the value that satisfies the first order condition is the unique minimum because the second order condition is satisfied. Then, it goes pretty straightforward. You know how to do that. Once you know the steps, how you have to proceed the argument, it is pretty straightforward. You know how to do that. But as I said, I wanted to challenge if you can distinguish those two concepts. What you have to prove, what is known, what is unknown. But some of you are still confused. And the sample criterion function, simple. I'm not going to do any detail. And C, moment criterion function for the GMM. There is no difference from part A, but the difference is we are starting from this moment function. And conceptually, we define moment function this way, and then we define another criterion function this way with a certain weighting matrix. And weighting matrix is the optimal weighting matrix is known to be this. Excuse me, it should be inverted here, 1 over sigma squared. So inverse should be applied to everything. Anyhow, you know, like the detail algebra is, you are good at algebra, so I don't worry about your algebra. But here, this is simply what we did. Just follow the basic structure. And the problem is to show its unique minimum. The process, you can do the same thing as we did in part A by showing the second order condition, but a more elegant way is to use strict positive definiteness. We know that by one of the assumptions, we know that this guy is strictly positive definite, right? And that means mathematically the strict positive definite matrix satisfies this. For any vector v, the quadratic form is always greater than 0 or equal to 0, and it equals to 0 only when the vector is 0. So 0 is the only solution that makes it 0. That means, in other words, if you think about this carefully, to minimize this function, v is the unique solution. So it is always non-negative, but 0 at only one point. That means 0 is the minimum, and it is unique. So we are applying this. So, and you know, this v is actually the moment function in our setup. So what we need to show here is the moment function is 0 only when beta equals to 0. Then the proof is the unique minimum is proven. And then now it is trivial. So equals to 0 is trivial, but its uniqueness will be again implied by another derivative. So the moment function is strictly decreasing because you can show the derivative is negative semi-definite, negative strictly definite. So it is strictly monotone. So there is only one point that satisfies 0 because the function is always decreasing. And finally, it's easy to be mistake the criterion function like this. I meant to say they are not equal. It's not wrong. It's not correct. It should be not equal. They are not equal, so they are different. You have to be careful. And this is the GMM, and this in the end becomes the OLS criterion function, but in general it doesn't mean anything here, right? And finally, in the sample criterion function, the optimal weighting matrix takes this form. Optimal weighting matrix theoretically is given by this, and as I said in the class, so expectation is not a problem. You may replace the expectation with sample average. So this is not a problem, but the problem is beta 0. Beta 0 is the true value. So we are, by the way, we are calculating this weighting matrix to estimate the true value. But to estimate the true value optimally, we need the true value. So you cannot solve that problem. So we usually use two-step approach. We have an preliminary or intermediate estimator for beta 0 in the first step, and use that to estimate the optimal weighting matrix, and use that optimal weighting matrix to again estimate beta here. However, in this case, in our case, we don't have that problem because beta 0 disappears. Does not have beta 0 here. But still, another problem you may think is sigma squared. It is unknown. It is also unknown. And sigma squared actually depends on beta 0. Without knowing beta 0, you cannot calculate sigma squared. But not a problem, because multiplying or dividing by a positive number does not change the estimation, right? Minimization problem remains the same with or without sigma squared, so you can ignore that. So if you ignore this, then you know how to handle this. Expected value of x prime inverse. Simply just replace expectation with sample mean. I did not write. Yeah. So usually we use this as an estimator for the optimal weighting matrix. So this is how we use the weighting matrix. And question 2, before going into the question, I will first set up a lemma to simplify a later part. So simply consider simple regression, regress A on B without intercept. Then we know the closed form solution, and actually I should have written more. And then you can calculate the variance of this, and everything is known. It is simple, right? And if you further include another variable, not a problem. You can regress A on B and C at the same time. So two regressors, not a problem. Closed form solutions given, and the variance also can be written as a matrix. So not a problem. We are going to use these kind of formula, for the later part. So think about this. Unrestricted model first. Unrestricted model. We only, by the way, let's look at the question. I'm going to, so there are 3 coefficients, alpha, beta, gamma, and everything else is simple. So mean 0 and all exogenous, full rank, and homoscedasticity. But we have an additional information. This is an assumption. This is true. And there is another assumption which is uncertain. This is hypothesis. This is hypothesis. This is assumption. Actually, they are similar, but they are playing different roles in the estimation. And then we know this is true, so we have to utilize this in our estimation. So technically, you may use this as a constraint in the minimization of least squares problem. That is good, but that's not the best way. That's not the best way. Like a better way, or more clever way, is just replacing alpha with 1 minus beta. Then you get this, and then so many of you have done up to this point, but you have to do one more step. Like this part, x1 should be rearranged, should be moved to the left hand side, because it's known. Its coefficient is known, so there is no reason for this to be here. You may treat it as a dependent variable. So now the left hand side is y minus x1, and on the right hand side, beta and gamma. But beta is the coefficient of a new regressor, x2 minus x1. And gamma is the same. So then you may interpret this equation as a regression of this guy on this and this, x2 minus 1 and x3. Only 2 variables. It's 2 regressor case, so its closed form solution is complicated but possible. We know how to obtain the closed form solution. Sorry for the messy algebra, but just and by the way, okay, so that's good. And another So some of you have done this well, but another hidden step to be complete is to show the classical linear regression assumptions for this guy. So for this equation, we have a new dependent variable and a new pair of regressors. So technically, we do not know if this regression satisfies the classical assumptions. We have to prove that. It's actually easy. First, to show the exogeneity, it's easy. It follows from the exogeneity of x1, x2, x3. And full rank condition. Full rank of this, I'm going to call this B and this as C. Full rank between B and C means they are not multicollinear. Multicollinearity or linearly independent. They are linearly independent, which is easily implied by the full rank condition of x1, x2, x3. I briefly wrote down a proof. That means I want to show that these two regressors are linearly independent. That's what I want to show. Now I'm going to assume that they were not linearly independent. So if they were linearly dependent, then it contradicts to assumption 5. Assumption 5 is the full rank among x1, x2, x3. So that means if B and C are linearly dependent, that means x1, x2, x3 are also linearly dependent. It's not that difficult to prove, right? So anyhow, like linear combinations should be linearly independent, technically, and then the unrestricted estimate, like the point and the conclusion is that the unrestricted model is a regression on two variables. That's it. It's as simple as that. And now we are going to the restricted model. It's even easier because we are including this as another assumption now. We use this as an assumption. And gamma further can be replaced by beta 0. Gamma is now replaced by beta. So that means alpha was already replaced by beta. So alpha is replaced, gamma is replaced. In the end, there is only one parameter, beta. Then rearrange these guys. Then again, the left-hand side do not have unknown coefficients. So at y minus x1 as before. And the right-hand side has only one regressor for beta. So beta depends on these guys. So it is a simple linear regression. Nothing more to explain. It's simple, pretty simple, easy to estimate. You know how to calculate the variance. So pretty simple. Now, wild test. Remember, wild test is based on the unrestricted estimators. We are comparing, simply speaking, we are going to compare beta and gamma, estimate beta and estimate gamma, and then see if they are the same or not. So we are going to focus on their difference. So we are going to use their difference, and we have to obtain their variance to standardize those guys. And then in the end, we know they are converging to chi-square. And degree of freedom equals to 1 because there is only one equation in the hypothesis, one dimension. And then how do we obtain the variance? It's algebra to obtain the final result. Algebra is 30, but to write that, it's not that difficult. We know the variance of the OLS estimator. Basically, it's OLS with two regressors, so it will take this form. If you calculate that matrix, then you can calculate the variance of beta and gamma as a two-dimensional vector. And then beta minus gamma, the difference, can be written as a linear combination of the vector. So the variance of beta minus gamma is also quadratic form of like this. So calculating that matrix can be annoying, very annoying, but it's doable. It's possible. I'm not going to do this. And C, you need to calculate, you need to derive the criterion-based test statistic. So criterion function Q and Q, like for the unrestricted model and the restricted model, are simply least squares. Least squares called criterion functions, and let's say these are their minimums. And we know unrestricted, because it's a minimization problem, unrestricted minimization is smaller than restricted minimization. So our test statistic will be based on this, right? And then the problem is, this is not the end of the story. We do not know how to standardize this. So there is no general formula to standardize these guys. But in this case, because this is OLS estimators, two OLS estimators, and you may apply the basic F statistic theory like this, right? So in the end, F statistic is one example of criterion-based function in the least squares case, and with the restriction on the coefficient. So we can apply that, and that's how we obtain the asymptotics. Okay, this is it. I think you did well in question 3. Let me see if I need to do anything on question 4, 3 and 4. See you later. Bye.